class is missing and then we are having lectures. That's not possible. Even if we are recording and doing all the things, this is kind of strongly recommended thing. Okay. So is my screen visible to you?
Yes, sir.
Yes.
Good.
Yes, sir.
Okay. So today in lecture 7, we are going to discuss some more things about this topic, digital electronics and circuits. So in the previous class, we have seen, if let us say we are given a lookup table and we are asked to design this based on our whatever knowledge we have earned so far in the course. So we saw that we have to look for the conditions when this function is getting true value, and we have to design on basis of that. So we came up with some design, and we also have to ensure that when we are simplifying, we not only look for the values for which the function is true, we also have to ensure that it is false whenever it is required to be. So any random minimization is not correct, and more about minimization we will learn actually. This is so far we have not done. Now some things we try to understand if we are trying to realize the circuits practically. So we have to have some electronic device, some semiconductor device, let us say diode or BJT or MOSFET, and using some resistance and capacitance sometimes, so we can realize these circuits. Now first we try to understand what is diode. So most of you are already aware about the PN junction diode, and when it is forward biased, when it is reverse biased. So these are the two conditions, on and off, which we are going to use for our circuits. So we are very much aware of what happens when we connect the diode in this fashion, let us say in the given circuit, and if we connect in reverse fashion over here, so we are very much sure that what's going to happen to this current. So somewhere when it is forward biased, it basically conducts, and whenever it is reverse biased, it basically blocks the voltage. Now we have seen the ideal characteristic of diode, which is drawn in red lines over here in the VI plane. So we see that ideally the diode will conduct any current, and ideally it will block any voltage, any negative voltage across it. But practically there are some differences from the ideal characteristic. So on the conduction side, we are not having the characteristic very much connected to the y-axis. There is some gap. So of course there is some forward bias voltage required. Some minimum 0.6 or 0.7 volts are required for making the diode conduct. And then further there is certain slope in the characteristic. It's not perfectly vertical line. So this slope indicates that there is some resistance element present over there. And on the negative side, we are seeing that it cannot, of course, any practical device cannot block infinite voltage, even air cannot block. So we have certain voltage after which the diode will break down and eventually start conducting. So this particular voltage is called the breakdown voltage. So after this, we cannot ensure that diode will be useful for the circuit anymore. But there are certain special diodes, let's say Zener diode, which are particularly made for this type of operation only. So the breakdown voltage is very, very less, sometimes 3.3 volts or 6.6 volts, and they are somehow made to go in this zone so that the particular voltage is maintained across that device or diode. So this is utilized in some of the voltage regulation circuits and all. Then we tried to see the equivalent circuit of diode. So when in open circuit, it's more or less like a open switch. So in the reverse biased condition, whenever the voltage across the diode is less than 0.6 volts or negative. So we can also say that it is not open circuit, but a very high resistance, let's say some 1 mega ohm or something like some 100 or 500 kilo ohm, something like that. So this is another thing which we need to keep in mind, because even if it is open, there is some current flowing across the device, some microampere, nanoampere current is flowing. So of course, that's not perfectly open. But more or less for our practical applications, we say that yes, the device is behaving like an open circuit, or you can say like a high resistance. So these both are equivalent. Now in the forward bias mode, when the voltage across the diode is more than 0.6 volts and it conducts, so the equivalent circuit is like one impedance coming over there, the one voltage coming over there and a resistance coming over there. So reverse, I mean, you have to see the direction of the current. So the EMF is actually opposite to the direction of the current, and resistance is available, which is basically giving the slope in that characteristic. So this value could be 20 ohm or something else, let's say 0.1 ohm. So it varies depending on what application we are having for the diode and how the manufacturer is making it. So if let's say we are dealing with circuits where all the resistances are of the order of 10 kilo ohm or few kilo ohm, then this 20 ohm or something is nothing. We are expecting currents of the order of milliamp. So it is okay to have 20 ohm or something. But whenever, let us say, we talk about power circuits where the current is going into few amps or tens of amps, so here we cannot afford to have 20 ohm. So we have to have lesser resistance for the diode. So 0.1 ohm or sometimes 1 milliohm, something like this, is deliberately designed for the diode. So that is how we manufacture and we play with parameters and we get the things done. So based on diode, we have seen the diode logic, and you can also call it register diode logic. So RDL you can call it. Of course, diode is not alone. Some other parameter, I mean some other element, let's say resistance is there. So here we have defined some levels, what we will assume as logic low and what we will assume as logic high. And in between whatever comes, that we will call as noise margin. So some gap should be there between the low and high. So that will give us some noise margin, that even if some noise is sitting on the voltage, it can clearly distinguish between the low and high voltages. So which is what we have seen over here for the diode logic or RDL logic. So 0 to 2 volts, we say that if the voltage is between this range, it is called as zero logic, or binary value is given as 0. Whereas if it goes between 3 and 5 volts, it is called as high logic or logic 1. Anything in between 2 and 3 volts is like a noise. We do not consider it anything. It's undefined. Am I clear so far?
Yes, sir.
Yes. Yes, sir.
So if I am going very fast, you can interrupt. You can tell me to slow down. No, sometimes while telling things, no, if no response is coming, I assume that you are perfectly taking all the things as it is. So you have to tell me that where you are going away from the things which I am telling you, where you are deviating from the track. Understanding my point?
Yes.
Yes.
Of course, there is certain difference between lab and class. When we are discussing things in lab, that is more like we are giving instructions. So when instructions are given, yes, of course, it will be little fast, like what happened yesterday. So kind of very, very fast it was, because there you are meant to do things, and then you feel like what all problems you are facing, what all no doubts you are getting, that you get after doing something in lab. Whereas in class, yes, I have to teach, so I can go as much as slow as possible. Clear? So you are free to interrupt anytime, and that is why you have to be attentive. Again, I am saying, everyone whosoever have not turned on their camera so far, please turn on. I am watching you on the other screen, so don't worry. And I am taking the screenshot every 5-10 minutes. That's automated in the system. So I'll be comparing like who was there 10 minutes back and who is not there now. Fine? Okay. So now coming to some designs using this RDL or diode logic. So let's say we try to manufacture or we try to fabricate the AND gate. So with two inputs. So we have given some circuit like this where some VCC voltage or 5 volts voltage is given, and through a resistance which may be of the order of 10 kilo ohm or something like that, and then the diodes are connected in this fashion. So we know for AND logic, we have to have both the voltages 1 for having the output 1. Isn't it? Any confusion in this? So you can see, even if any one voltage is not high, or even if any one voltage is not having sufficient voltage which should be called as 1, then the logic at this point will be equivalent to the zero logic or low logic. Understanding my point? The other diode which is having input of logic 1 will be in the reverse bias mode. It will not conduct. Clear? No, this thing we have seen last time, and same thing you are doing in lab also, right? Yes or no?
Yes.
Fine. Now, similarly, we tried to have OR logic also. So we had the diodes and resistance connected in this fashion, and we know that OR logic will be 0 only when both the inputs are 0. For all other cases, it is true. For all other cases, it is 1. Understanding my point? So we have seen when both the logics are 0, then only these two would be in reverse conduction mode. So this will not. Otherwise, any one conducts, so the logic will reach over here and it will reverse block the other one. So it doesn't matter whether the other one is blocked or not. The voltage at this point would be corresponding to logic 1 or high logic. This we have seen last time. Any confusion, any doubt in this?
No, sir.
Ask now, because
Yes, sir.
after this I will move into next part of the logic design. This is fine, right?
Yes,
Okay.
sir.
Now we
Yes,
have
sir.
seen the problem with the RDL logic is the diode drop which is coming, which is very, very high, 0.6 volts. So sometimes when we are giving low logic, the output is actually a little bit increased, although it is fine that within 2 volts it is again low logic. But let us say you connect one more gate, it may become 2.2. So which is going into undefined zone, and slowly it may go to high also. It may go. So which is incorrect. So these are some of the problems, and also we do not have the liberty of making NOT gate in this logic. So this possibility is not there. So we are having some constraints, and that is why this was not a very popular way of designing any gates or something. And we quickly move to the next semiconductor device, which is called BJT. Now, let us discuss some properties about BJT, and then we go by designing some gates on basis of this. So what do you mean by BJT? Responses?
Bipolar junction transistor.
Yeah? Dhruv?
Bipolar junction transistor.
Yes, that's the name. What else?
So basically, it's a three-terminal semiconductor device.
One by one. Saransh?
So it's a three-terminal semiconductor device,
Okay, that's
and
a
there
very
is
good description.
collector, base, and emitter. These are the terminals there.
Yes, very nice description. So it has 3 terminals. We can say there is base, collector, and emitter. Now, diode we have seen that was kind of uncontrolled, no? There was no control over it. The circuit was driving the diode. Here we have something which is basically controlled. So controlled through something, we may call it as base. So this could be like a trigger signal. When you are giving, this device may turn on, or not may, but it will turn on. And if you remove this gate signal or base signal, then it will go off. Understanding my point? Now, theoretically speaking, it can be represented like this. Two diodes connected in this fashion. But it is very, very different when you connect when you make this configuration on the same substrate. So this is also having this PN and then PN. That's why two bipolar junction that is coming. No, the polarities are different. So when you make it on the same substrate, the properties are much different than connecting diodes in this fashion. Understanding my point? So theoretically, or no, just to say that okay, BJT can be seen as two diodes connected like this, but it is much more different when you manufacture or when you make it on the same substrate with these NPN kind of dopings. So what we have basically over here, so okay, first we all know that this is the kind of symbol used for the BJT. So this arrow indicates basically the direction of current. So we have the base terminal over here, then we have the collector and the emitter terminals. So what happens? This is basically a current control device. And this current control, when I'm saying this, the control is given through the base, which means this I base is basically controlling how this BJT or how this device is going to behave. Understanding my point? So now there are three zones. No, we have discussed in one of the previous classes also that if we draw the VI characteristic of BJT, again, if you go for ideal characteristic and the practical characteristic. So ideal characteristic is it doesn't operate in this zone. Understanding my point? You cannot expect to apply a negative voltage over here and expect it to behave properly. We cannot apply negative voltage for a good response. It only operates in this zone, in this quadrant, you can say, where the voltage is also positive and current is also positive. So positive, I mean this direction, and positive, I mean this polarity. Understanding my point? Now, the ideal characteristic says that it can block if you do not give any base current or any trigger signal. It can block any voltage and it can conduct any current when the base signal, appropriate base signal is given. But of course, practically when we are using, there are basically three zones for this device. So the practical characteristic will deviate little bit and it will go something like this. So this portion is little bit exaggerated for clarity. Something like this. So these levels what we are drawing, this is dependent on the base current. IB1, IB2, IB3 and so on. Now three zones what we can identify over here is, first one is this zone, second one, so let me draw one more line over here. So very small current but large blocking capability. So the second zone is this, and third zone is what we are getting with the different values of IB. Understanding my point? Now this first zone is called as saturation zone. So you can see the VC value is very small over here, whereas the current is very high. Understanding my point? The second zone is called cutoff zone, where the current value is very small, only some leakage current, but the voltage is very large. This is VC voltage I am talking about. The voltage is very large. So this is kind of, it is blocking this voltage, not allowing much current to flow through it. The third zone, this is called linear zone or active zone. Here, the device is behaving according to what base current you are giving. So the VC value or IC value is dependent on how much base current you are pumping over there. So somewhere it is related to another parameter of the BJT. The IB and IC are related through another parameter of BJT, which is called the beta coefficient or HFE coefficient of the BJT. Understanding my point?
Yes, sir.
Up to this you are clear, right?
Yes, sir.
Must have learned in some other classes as well, right?
Yes.
Now, if we have to classify the values of IB which drives this device into different zones. So first let us say cutoff zone, then we have active zone, and then we have saturation zone. So can you say what are the values which will drive the device in different zones? What should be the value of IB for cutoff zone?
Sir, approximately
0.
Yes.
Sir, 0.
Not giving any base current, then the device will remain in the cutoff zone. It will not conduct anything. The collector emitter, this current will not flow. Understanding my point? Now, what happens in active zone? What should be the IB? Or is it related to something with the transistor, some parameter or something? Any idea? Yes? Say whatever you know, you say, don't worry. This is not, we are not having any examination. This is only class. You are learning. If you make mistake, you learn more. Only in the class, not in exam.
Base junction should be forward biased and a collector base junction should be reverse biased for active zone.
That is fine, but what should be the value of IB? How can we relate it with the transistor parameters or other things?
IC by beta.
Yes, exactly. This is the linear relationship what we are talking about. So most of the amplifiers, what we see, they operate in this linear zone. So depending on the base current, your collector current is changed, and so is your VCE voltage. We will see how that is changing. Now the saturation zone, what happens here? What happens in the saturation zone?
VC tends to 0.
VC is 0.
Okay, that is all fine, but I am talking about IB, no, because this is our, what to say, the driving force for the BJT.
I is equal to I.
Okay, what else?
VCC by R.
Okay, what else? Whenever you violate this condition, whenever you cross this boundary, let's say you are pumping enough current in the base, okay, more than what the IC max would be there in the circuit divided by beta. If you pump more than that in the base, the device is forced into saturation zone. Understanding my point? So this is how we bias the BJT for the different zones. If you are pumping zero current, it will remain in the cutoff zone. If you give only enough current so that it is related to your IC in this linear fashion, then it will operate in the linear zone or active zone. But if you cross this limit, if you pump more than what this relation can permit, then this will go into saturation zone. So our gates will operate only in the first and in this third zone. The second is not recommended, or second is not used. Only during some transition time, let us say if you are increasing from 0 to this third level, in between for some time it will be in this active zone. That is okay, that is permitted. but not for steady state kind of condition. Understanding my point? Yes or no?
Yes, sir.
Yes, sir.
Now let us see this. Once we have the BGTC, these things are something, if you learn at this stage, no, this will give you a lot of things related to all your whatever things you are going to do in future classes, be it power electronics, be it any other electronics related course. So it is going to be useful everywhere. If you are designing any circuit or doing anything relevant to your VLSI or something, whatever. So these basic fundamentals are going to work everywhere. So pay attention if you are targeting some core kind of career in future. So now let us try to see how this is happening. Let's say we have some common emitter kind of configuration over here. So we have some VCC voltage given, and let's say this resistance is R2, this is R1, and this has beta coefficient, and we are applying some voltage over here, let's say VB. So, and we are trying to see the voltage over here. So basically this is our V out, we can say, or VCE we can say, so which is basically this voltage. Now if you write the equations for this, and assuming that the current flowing over here is IC, here it is IE, here it is IB. So let's assume that IC is beta times of IB. That is what is there as of now. Now, what will be this voltage VC if you write the KVL for this circuit? What will be VC?
VCC minus ICR1.
ICR.
VCC minus IC into R1. Now, you can also write in terms of IB. So VCC minus beta times of IB times of R1, isn't it?
Yes,
So,
sir.
which means if you keep on increasing your IB, what will happen? Your VC will keep on reducing, isn't it? Simple thing, right? Nothing very complicated. Now, tell me, what could be the minimum value of VC? Up to what value you can go? Can it be negative? You keep on giving some current at IB, and you keep on reducing this value of VC. What is the lowest VC value which you can attain? Can you suggest? Yes?
Sir, 0.
Okay, that is one.
Theoretically,
Possibility is 0. Why not negative? What is problem with this?
so current should flow in the opposite direction to make it negative, which I think is not possible.
Not possible. Okay, so actually even 0 it also not possible. There is a limit for this VC voltage, what minimum value it can attain, and that is what is called VC saturation. Understanding my point? In the characteristic, if you see, the VC value of course cannot be negative, that is what we have said, and the minimum value what it can attain is this small VC saturation. So the value of this VC sat could be 0.2 volts or something like that for a typical BJT. Understanding my point? Now, if that is the case, if that is what we are going to attain as the minimum value, what happens to this equation? Is KVL not applied over there? Is KVL not applicable? KVL goes wrong. Let's say,
In that case, IB will be maximum.
yeah,
So maybe beta changes.
Okay, that is one thing. Good, interesting.
Maybe IB will be maximum.
Yeah, so let us say I am having IB1 as the current at which I have attained VC. Now what if I pump IB more than IB1? What will happen?
The beta will reduce.
Okay, that is good. So what I mentioned earlier, no, this equation what is there, this is valid only for what reason?
Active
Linear
reason.
or active
reason.
reason. So simply what happens that this equation ceases to exist. This equation becomes invalid the moment you reach this value VC sat. So this equation itself will not be valid. It doesn't mean that KVL is not valid. This part you will not be able to write. You will not be allowed to write. You can only write VC sat is equal to VCC minus IC into R1. IC you cannot write as beta IB. This equation ceases to exist or ceases to be valid. Understanding my point? Now, what will be the result of this? Now the IC is not dependent on I beta. It is dependent on the circuit. Understanding my point? So, if you have this circuit over here where your transistor is drawn into the saturation zone and this is VCE sat R1, R2, this is some VB, this is grounded. So here your IC will be dictated by VCC minus VCE sat because both these things are fixed now divided by R1. Now this is the equation which will govern the value of IC. Understanding my point? This is very, very important thing to understand how your IC is governed. Now once you know that how you are getting the value of IC, you can properly choose the value of R2 such that your I beta is always following this kind of relation so that your zone or saturation zone remains always true. You are always in the saturation zone whenever you are driving it. Or if you remove this VB, then you go into cutoff zone. Understanding my point? We will come to this, how we design R1 and R2 in a little while. So now, once we have done this, now let us see what is happening to this circuit. This we can call as logic inverter. Okay, so far we have not designed the R1, R2 values. I will come to that. Logic inverter, or simply we can say NOT gate. Now the same configuration what we were using over here. Now let me give some input, let's say Vx, and let me have the output over here as Vz, and here we have VCC. So the gates what we design over here, these are called register transistor logic. Or we simply call as RTL. Understanding my point? So we are using transistor and some set of resistors to design our gates. So this is what we are talking about. This was one of the first practical logic gates which were possible to manufacture, and they were also used for some period of time. And soon we migrated to other better options. That also we will see shortly. Now in this RTL logic, what we are doing when we are making NOT. So what is happening? Let us say, assuming that we are giving sufficient voltage. So this is R2, this is R1. We are giving sufficient voltage as Vx, and we are having appropriate values of R1 and R2 such that this is always operating in the saturation zone or in the cutoff zone. Now, assuming that this is true, we will see how to design that. That is next thing. Now, let's say if you are giving value 1 over here, what would you get over here? Value 1 means, let us say you are giving 5 volts. Now, what value you will get over here at VZ? What voltage?
The VC saturation.
Yes. So approximately 0.2 volts, which is actually logic 0 or logic low. So you are giving high and what you are getting at output is low. So what is happening? Your logic is getting inverted. Similarly, if you give a logic low over here, which means 0 volts, what you will get over here? So this will be completely blocking. IC will not flow. So basically, you will get VCC voltage, which is pulled up through this resistance. So the output will be VCC, or you can say high logic. So whenever you are giving low, you are getting high. Understanding my point? So which is simple logic for the NOT gate. Whenever you are giving 1, you are getting 0. Whenever you are giving 0, you are getting 1. So that is why this configuration is called logic inverter or NOT gate. This is one of the first constraints what we had in the resistor diode logic. Now we are able to make our NOT gate over here, and we will make more gates using this kind of arrangement. Now, certain things which we need to define. What is called as logic low, similar to our diode logic. No, we have to define the levels. What is called as logic low, what is called as logic high. So first of all, we have to define VCC for RTL. So anything when we are taking, we must have the voltage for which we are operating our circuit. So for RTL circuit, the operating voltage is 5 volts. Even for the higher and better configurations, TTL, CMOS and all that, we have plus 5 volt as our operating voltage. Understanding my point? Now, the second thing is which voltage we define as logic low. So which voltage should be defined? Can you suggest?
VC saturation.
How it's related to VC saturation? See, it is about what input you give over here. So basically what happens, your base and emitter, these are basically what? Forming a PN junction diode, right? Now what is the drop across this diode? Minimum voltage after which this will start conducting?
0.7.
0.6. Isn't it? If you give any voltage more than 0.6, there is possibility that this may conduct. I'm not saying that it will go into this saturation zone or what, but at least it may start conducting. There is possibility, right? So we safely operate the low logic within this 0 and 0.5 volt. Anything beyond this we called as ambiguous. So 0.6, 0.7, all these things, it may be risky. It may drive your transistor into linear zone, may drive into saturation zone also, if you are having very small values of R1, R2 and all. Understanding my point? So then we define our high logic. So there has to be some gap between the highest low logic voltage and lowest high logic voltage, and that gap we keep as 1.5 volts gap. So anything coming between 2 and 5 volts, that we call as high logic. You are seeing this gap, right? The maximum voltage for the low logic and the lowest voltage for the high logic. Understanding or not? Yes or no? Clearly.
Yes, sir.
Yes, sir.
We are
Yes.
giving this noise margin of 1.5 volts. Now this is the condition which is followed for the RTL logic. This may not be true for TTL or CMOS entirely. Only VCC value was true for this. but the RTL logic operates with this kind of configuration. So which means at the input, if you want to remain relevant for the logic low, you have to keep your voltage within 0.5. And if you want to have a relevant high value for the logic high, you have to give at least 2 volts. Anything in between will be taken as undefined. Clear? Yes or no?
Yes, sir.
Yes.
Okay. Now let us try to see what could be the values of R1 and R2. Is it all right or not? Are you understanding, following these points?
Yes, sir.
Yes, sir.
Yes, sir.
It's looking interesting or what? Is going very boring and monotonous? Say clearly, yes or no, what?
Yes, sir. Interesting.
Okay, good. What is interesting, Lakshit?
You're learning new things.
Good, good, good. I'm happy to hear that you are learning new things. Very nice. Okay. I hope that is true for the most of the class. I am not saying for everyone. Okay, now let us see how to design the values of, see, when you are designing any circuit, each and every parameter you have to understand how you are designing, why you are putting that value. No, these questions are not just important from the examination point of view, but whenever you go in front of any interviewer or anyone else, simply they will ask why you are putting this resistance value or why you are putting this particular voltage value. So I may give you some example. Let us say you have a simple LED. Okay. So, okay, this LED can operate with 5 volt or something, but we cannot connect just 5 volt across the LED directly. No? There has to be some limitation on the current what this LED can take. So there people have done blunders of connecting this LED across 5 volts directly in an interview or something. Now imagine after completing your BTech or you are about to complete your BTech, you have learned all these circuits and all these things, and you connect the LED across the 5 volts directly. What will happen? Yes, it will glow for maybe a very small time, for maybe 10 millisecond or something. After that, it will burn out. It cannot take that much current. Okay, so to avoid such blunders, please pay attention. Fine. So I do not want you to make such blunders. At least choose appropriate values of resistance. Why we are choosing, that is what we learn in all these classes. Now let us say we have to design the circuit parameters. So what are the circuit parameters? It's only resistance over there. That's the only circuit parameter what we have. Let's say this is R1, R2, and we are having some input voltage over here. This is connected to ground. This is VCC over here. Now, what should be the value of R1? Any guess? Okay, I know yesterday's lab class has given a lot of hint, but can you guess what should be the value of R1? Or how do we
10
choose?
kilo ohm.
Hmm? Yeah. Yes, someone said something. What happened?
So it should be high, something in kilo ohms.
Yes. So when you say high, my first question would be, what do you define as high? See, for the logic, we are defining what is high. Now for resistance, what do you define as high? Is 100 ohm high for you? Is 1 kilo ohm high for you? Or 100 kilo ohm is high for you? Or 1 mega ohm is high for you? What is high? What do you mean by high? Respond quickly. Okay, everybody is staring at the screen. Just say something, no? You all are doing the same degree, right? Not someone is doing BTech, someone is doing something else. So you all are equally eligible to say something. You are very much welcome to put forth your opinion over here in the class.
The value which
Sir, I
makes
think when
the
One by one. Yes, Saransh? Okay, should I start taking names for asking someone? Speak something. Don't worry about what
Sir,
you can say will be wrong. Yes.
it should be a value which makes the potential drop comparable to VCC.
Yes, very good. That is very, very good response, I would say. But there is something more which you need to understand. See, this whatever current flows over here, if you are driving this into VCE SAT, obviously any current flowing over here will make this drop, most of the drop across this resistance. Isn't it? That is what the KVL says. What is the drop across this resistance? That is always VCC minus VCE SAT. That is the voltage across the resistor R1. Isn't it? Irrespective of what value of resistance you take, this will always be true as long as you are driving it in the saturation zone. Even if it is not in saturation zone, whatever is the VCE value over here, the remaining voltage will always be dropped across this R1. This is simple KVL, no? You have learned in
Yes,
your
sir.
12th class. Now what
Yes,
should be
sir,
the
yes.
value of R1? Say some numbers. No, before having any calculation, before having anything in mind, you should be able to suggest that, okay, yeah, this could be a probable value. You should have a feeling for it. Okay, yes, this looks okay. For this kind of circuit, this is a good value. Without doing much computation, you should be able to say that. So someone was saying 10 kilo ohm. Fine. I say this is okay. There is no problem in that. At least you have some starting point. Now we put this value in the circuit, we see how it is behaving, then we change the value if it is not behaving in the proper manner. Isn't
I
it?
think
Yes or no?
R1 will be VCC minus VC upon beta IB, and beta is in range of something 1000
Again, I am
to
saying we are
20
not talking
kilo.
about linear zone, Saransh.
Sorry, sir.
Yeah, we are not talking about linear zone, right? All our discussions we will try to keep such that we are making our gate, we are trying
Sir,
to
IC
somehow design.
is
We are
almost
not designing the amplifier. This you have to understand very clearly. Okay, so I stop over here with these open questions in front of you. Next class we will start from here itself. That means tomorrow. Fine? Not tomorrow, I think the Saturday. Tomorrow is holiday. So Saturday we will start from here at the same time, 10 a.m. Fine? Just
Yes,
think
sir.
about it. Think little bit about it, how to design, what to do, how to choose the appropriate value, what should be called as appropriate value. So quickly,